All right. So obviously last week we took the exam. I recorded or posted a recorded lecture of chapter 4 to try to keep us on pace. So, like I said, hopefully you watched that. If not, make sure you do watch it because we're going to kind of pick up from the end of that recording and finish up chapter 4 here, and then hopefully roll into 11 at that point. So, what was in that sort of last lecture there was again we were talking about atomic numbers. Which is again our number of protons in an atom. We're also talking about our mass numbers, which is our number of protons plus our number of neutrons. Remember, you can basically subtract both of those to get the number of neutrons. When you calculate anything like mass number, atomic number, number of protons, electrons, and neutrons, again, they all should really be whole numbers uh, and positive whole numbers. The only one that you can get from the periodic table there is, again, the atomic number, which is the number that comes above the symbol there is our atomic number. Remember that the mass number is not on the periodic table, so it's not the number on the bottom. That is the atomic mass. So you should be able to sort of calculate all those things. We also talked in that recording there about the periodic table itself and the different parts of the periodic table. And essentially we have groups, and groups go from top to bottom as in the periodic table. And we number our groups. We use the representative numbering, which is the A numbering, and that is group 1 on the far left there. And it actually starts with lithium, not hydrogen. Right next door is group 2, and then we skip the middle part. And then where boron is, that is group 3, 4, 5, 6, 7, and 8. Periods, they go left to right there on the periodic table, and there is, like 7 periods on the periodic table, heading in that kind of direction. There's also special names for these groups. Group 1 is the alkali metals. Group 2 is the alkaline earth metals. Group 7 is the, not the halogens, it is the halogens. Group 7 is the halogens. Group 8 there is the noble gases. Periodic table also broken up like a little staircase action happening there. Thank you. To the left of the staircase is our metals, which are good conductors of heat and electricity. They're usually very shiny. To the upper right of the kind of staircase there are our nonmetals, which have sort of the opposite sort of characteristics. They are bad conductors of heat and electricity. They're dull, they're brittle. And really on the staircase here are our semi-metals. They're sometimes referred to as metalloids. Thank you. And those guys are guys that have properties that sort of fall between metals and non-metals. So the same element has both a property that's very metal-like, and it could also have properties that are very sort of non-metal-like. And it makes sense sort of their positioning as it sort of transitions from metals to non-metals as you kind of cross over that staircase, kind of heading upwards. Between group 2 and 3 there is our transition metals. And as we'll talk about with sort of naming, those are guys that can have more than one type of charge. The other thing that we touched upon along with sort of atoms and atomic mass and mass number and atomic number was ions. And ions have things that have charges, and they typically are 2 types of ions. We have cations, which are positively charged, and we have anions, which are negatively charged. And for the most part, metals are typically the ones that will make cations, and anions are typically your nonmetals. There's typically the ones that will make that. That, by the way, is pretty much the attractive forces between those two is electrostatic attraction, which makes an ionic bond. A reminder that nothing on the periodic table has a bond, and nothing on the periodic table has a charge until they kind of get together, a metal and a non-metal, when they make charges. So things on the periodic table by themselves that are uncombined are neutral. They do not have charges. Again, they really only kind of get charges when they come together. This is achieved sort of a cation by the loss of electrons, while an anion is really gaining of electrons. When you lose electrons, for example, in a cation, you then have more protons than electrons, so you have more positive things than negative things, so you become positively charged. When you gain electrons in an anion, you now have more electrons than protons, so you have more negative things than positive things. So you end up with an overall negative charge. And usually what happens, as we'll talk about, is the metal kind of gives its electrons up to the non-metal, and that's why, again, the metal becomes positively charged, the non-metal becomes negatively charged, and then they're attracted to each other, and that's essentially what makes an ionic compound. Any questions on any of that there? So again, if you haven't watched that video, make sure you do, and we're going to pick it up here towards the end of that video. Now, speaking of things with charges, as I mentioned before, things on the periodic table do not have charges when they're by themselves, but when they do gain charges, some things on the periodic table have, I'll say, sort of a fixed charge depending on what it is. So everybody in group 1, which is right here, again, starting with lithium, everybody there will make a +1 charge when they do make a charge. Right next door in group 2, those guys will make a +2 charge. I would say for the most part for group 3, it's aluminum is really the one that you're going to see that's going to be a +3 charge. These guys could do a couple other charges besides those things. So really, most of the time, it's aluminum there in group 3 that we're talking about. We actually skip group 4. There's really no good sort of pattern. Group 5 actually are -3 in terms of their charges, and those are the nonmetals like nitrogen, phosphorus. Those guys are what we're talking about there. Group 6 will make a -2, and group 7 will make a -1. Remember, the staircase kind of comes down in this direction. So again, when we're talking negative charges, we're talking above the staircase there in terms of our nonmetals. Actually, below the staircase, for example, like where lead is, antimony, SN, those guys are metals, and they actually make up more positive type charge. So again, negative charges above the staircase where the metalloids are and our non-metal region. So it's basically +1, +2, skip, +3, and skip one more, -3, -2, -1, going that way. These transition metals here typically can make a variety of charges, but there actually are 3 transition metals which actually do just make a fixed type of charge when they do make charges, and that is our friend here, zinc and cadmium, and then hang a right or left there to silver. Zinc and cadmium, they both will, when they make charges, make a +2 charge. Silver here, +1 charge. So silver will make a +1 charge. Zinc and cadmium will make a +2 charge. Pretty much everybody else in that transition metal region has the ability, like I said before, to kind of make a variety of sort of charges. It can make a +2, for example, or +3, +1, +2, depending on the situation. Any questions on that there? These are also really good things to know as we get into naming, knowing the charges that these things make. It also will be very helpful, obviously, when we get there. Yeah, zinc and cadmium are +2. Then if you hang a left, silver is going to be +1. Yeah. Other questions? Now, compounds that contain ions can conduct electricity. And when we talk about those things, those are sometimes referred to as electrolytes. And electrolytes are solutions that when they kind of break apart into the solution will actually break apart into ions, and they will have ions that are floating around in that solution. It's actually the presence of those ions that help it conduct electricity. So those positive charged ions, negative charged ions that are floating around is what helps it basically conduct electricity. And when we talk about electrolytes, there's really a few different types of electrolytes. There is a strong electrolyte. And a strong electrolyte will 100% break apart into ions in solution. So for example, if you had technically a sodium chloride solution, which is pretty much what the aqueous symbol means. The AQ means that it's aqueous. It's basically a water environment. When you have that sodium chloride solution, what you really have in that actual solution is 100% these ions floating around. So if you were to look at that solution, all you would technically see are sodium ions and chloride ions basically floating around. You would have none of the whole unit still together. So it would completely break apart 100% into ions as it's floating around in the solution. And because of that, there's such a large amount of ions that it's going to conduct electricity really, really well. So a very common experiment sometimes people will do with this is they'll take a light bulb that has a couple of electrodes hooked up to it. And if you were to put those electrodes into a strong electrolyte solution, the light bulb would turn on very, very brightly. So it would conduct electricity really well. The light bulb will turn on, be very, very bright. Now, there's also weak electrolytes. And weak electrolytes actually will mainly stay together, but will produce some ions in solution. So if you took something like hydrofluoric acid, which is actually a weak acid and also a weak electrolyte, it will break apart into H plus and F minus. Now in this case, you're going to get a little of these guys in that solution, but mainly what you're going to have in that solution is actually the whole thing still together. So unlike up here where you got none of that there, it will break apart. So if you were to look at that solution, what you'd actually mainly see in that solution is HF molecules floating around with a little bit of ions floating around in that solution. So because it's still able to produce some ions, is still able to conduct electricity. It will not be able to conduct electricity anywhere near a strong electrolyte because it has less ions present, but it would still be able to sort of conduct electricity. If you use that sort of example with the light bulb like I was just talking about, and you took the electrodes that were hooked up to a light bulb into a weak electrolyte solution, the light bulb would turn on, but it would look really dim, almost like it's dying. Yeah, so, but it would have enough to power it up. It would be very, very dim as opposed to a very bright light bulb that you would see in a strong electrolyte because of all the ions that are basically floating around. So since there's still ions. These reactions, you also typically see a different arrow. That is a reversible reaction. And then it basically has two directions. It has a forward direction where it goes from reactants to products. And eventually in these type of reactions, what actually happens is the products come back together and they head in the opposite direction and they go in the reverse direction. And it's really like a two-way street, basically, in this case. It will eventually reach equilibrium, which means the rate of the forward reaction will equal the rate of the reverse reaction, and also the subject of basically Chem 1B, pretty much the whole semester, equilibrium. So these type of reactions will go in both directions. They'll eventually come to equilibrium, which again doesn't mean they have the same amount on each side. It just means they're moving in terms of rate equal. And what that'll essentially do is lock everybody into place where they're at when it reaches equilibrium, because just as quick as you go one way, the other way will kind of come back and nothing will change basically on either side of it. Yeah.
So for the strong electrolytes.
Yeah.
Talking about the NaCl.
Yeah.
You're saying those separate completely.
Completely.
NaCl.
Ions. So it's basically aqueous. This is, by the way, this as we'll talk about, this is really where you find ions. Basically, if you have something that's like positively charged, negatively charged, you basically, for the most part, find them in a solution floating around freely in there. And in the case of sodium chloride, 100% of that sodium chloride, they're not going to be attracted to each other anymore. Because what's actually going to happen and why it dissolves is there's so much water molecules. It's like one of the only things that could kind of strip them apart from each other. That's a really strong attractive force, but just the sheer amount of water molecules there are, they're able to kind of pluck them away from each other. And the water molecules actually surround the ions, and that keeps them from coming back together. And that's what really, when it dissolves. So for example, we had like some salt water, I think we did earlier on, right? And you took the salt and dissolved in the water. It didn't really disappear. It's just that all the water molecules surrounded those ions. and it was no longer visible to us. We could no longer see it. It reappeared when you heated it because you got rid of all those water molecules, right? They evaporated off, and now there's no water molecules to keep them apart. The sodium ion and chloride ion are going to cling back together and make that solid, and that's why the solids, for example, reappeared when you heated that sort of salt water and evaporated off. Other questions? The last type of electrolyte is a non-electrolyte, and a non-electrolyte basically will dissolve in solution, but it will stay together. No ions. So because there's no ions, it will dissolve. So for example, sugar is an example of that, right? You take some sugar, it's going to dissolve. But sugar is covalently bonded. There's no ions that form when it dissolves. It stays together. And because there's no ions, it does not conduct electricity. So does not conduct. So if you take that light bulb example and you stuck it into like sugar water, the light bulb will not go off at all. It won't even be dim or anything like that. Again, here, a weak electrolyte will still conduct. And obviously a good conductor of electricity. And it's really, again, the presence of ions that help really conduct electricity. So in a non-electrolyte, because there's no ions, you get pretty much no electricity conducted. Yeah. It could dissolve because, for example, sugar has a lot of OH groups on it, for example, and those are very attracted to water. It's able to interact well with water and allows it to dissolve. But when it dissolves, unlike sodium chloride, the whole thing stays together and dissolves as like a whole unit, as opposed to when sodium chloride dissolves, they actually break apart and individually dissolve as ions in that case. And we'll talk about it. It has to do with, for example, sugar. I won't draw all of sugar, but sugar has this OH sort of group. And that OH group is, if you just think about what water looks like, pretty much the same deal as water. And they're able to, as we'll talk about in a later chapter, what is known as hydrogen bond with each other. And because basically sugar is littered with a ton of OH groups all over it, even though it's a larger molecule, it makes it really, really soluble in water because it's able to interact. And that's what you need for things to dissolve in each other, is for them to basically be able to interact well with each other. And that's why it happens. But the way it does that is, if this was our sugar, all the water molecules basically will just surround the whole thing, and that sugar molecule basically stays intact. As opposed with the sodium, what ends up happening is the sodium and the chloride, the water molecules surround each of these individual ions. And that's what kind of keeps them apart. And they're actually able to kind of pluck off the individual ions from each other. Other questions? Yeah. Now, water is a really bad conductor of electricity, right? Pure water is a bad conductor of electricity because it has no ions in it, right? Just so you know, though, right? Your shower is not pure water, right? You actually put ions in it to clean it. So, when you take a shower, that's why you don't want to, blow dry your hair at the same time, because you will get electrocuted. Don't do that. But if you have pure water, it's actually a bad conductor of electricity. As you can see there on the left, it has no ions, so the light bulb will not go off. If you sprinkle a little bit of sodium chloride in there, those positive and negative ions that are floating around that solution, again, able to basically conduct electricity really, really well there. And a weak electrolyte would be in the middle. Again, the light bulb would go off, but it would be very, very dim in terms of that. This is basically what ionic compound sort of looks like. They are attracted to each other through electrostatic attraction. They're in this three-dimensional shape. So I was talking about kind of the water coming in. Because there's so many water molecules coming in, they're able to kind of pluck off from the solid these individual ions. You help it along, right? Because when you go to dissolve something, you typically start to stir it, right? And when you're stirring it, you're throwing water all over that solid, and you're also adding some energy, which is going to help in the process of them kind of popping off those ions along the way. Now, another thing that we sort of talked about in that last lecture is how we go about, for example, naming ions a little bit, and we're going to get into really more specific ones. But in general, if you have a cation, which is positively charged, we usually will use the whole name of the ion. So if we had something like Na plus, that would be our sodium ion. And if you have an anion, which is our negatively charged guys, we actually take the root of the nonmetal name, but we drop the last part and add IDE to it. So for example, Cl minus, Cl is chlorine. We drop the last part of chlorine, and that becomes the chloride IDE ion. Sometimes we do go a little bit more than the last little bit of the name. So oxygen becomes the oxide IDE ion. So when we have negatively charged guys, we kind of drop the last part of the name. We add IDE to it when we're talking about the ion itself. And positive guys, we pretty much use the whole metal name for that. And there's a few different things we do for guys in the middle, transition metals. But for the most part, we still use the whole name along the way. But when a positive ion and a negative ion come together, when you put them together to make an ionic compound, it should always be equal to 0, the overall charge. So you want to put the positive guy and negative guy together in the simplest way that will get you to basically no charge. So for example, here, the sodium and the chloride, that is a +1, -1. We just need one of each of them, and we get sodium chloride as our formula for our ionic compound. When you write the formula for an ionic compound, it does not have a charge, but it is made up of two things that do have charges, which is a cation and an anion. So even though we write NaCl that does not have a charge on the formula, it is actually made up of two things that do have charges. When we look at calcium, which is group 2, that is a +2, and chloride, which is group 7, is a -1. So when we put this together, we actually need more of the chloride. That's going to give us a +2 for the calcium and a -2 overall for the chlorides. And really at this point, all I have to do is add up what you got there. I got 1 calcium and 2 chlorides. Yeah, so basically remember the guy on the bottom, the subscript goes to the element to the left, right? So the 2 goes to the Cl. Nothing written means 1 for the calcium when you do that. So you want to make sure that you always balance those out in the simplest way possible. Sometimes people are taught to do this, which is just bring the charges down, and that will become your subscripts. And that does work like 92% of the time. So if you're good with that, you could just blindly do that. But if you want to maybe get it right all the time, you want to think about balancing out the charge correctly and not just blindly kind of swapping the things down or up. It's very commonly taught that way, like just bring those things down and you'll get the subscript. Again, 90 some odd percent of the time, 92, 93% of the time, but you might want it all the time. By the way, this would be first name here, calcium, whole name of the metal. Chloride would be this guy. So that would be calcium chloride. This guy obviously would be sodium, and the Cl would be chloride in this case. So again, that is how the name, yeah. It's a good question. So the answer for now, we're going to get into really the rules of naming coming up in a few chapters, but the rules is whenever you have something like this, that's a positive and negative guy together, which is a metal and non-metal and ionic compound, you never use prefixes. So it doesn't matter, for example, that there's 2 Cls there. You don't use a prefix. You could have 40 of them. It doesn't really matter. Also on the first guy as well, if you have more than one, you don't use a prefix. So one of the rules of how you name these type of compounds that we're specifically looking at here is pretty much that. You take the whole name of the first guy, ID, the second guy, doesn't matter how many of each of those you have in this case. Other questions? Yeah. It is not in this case because it's aqueous, so it's floating around the solution. It is when it's by itself. So if it wasn't combined with, say, sodium, it is diatomic, it is Cl2, it would be a gas, and it would not have a charge in that case either. because Cl2 again is naturally how it comes. So remember, these things only have charges when they hook up between a metal and non-metal. And how the chloride actually gets the charge is the sodium donates it over. So in that case, for example, what you really have is something like this. Sodium plus your chlorine. Yeah. Makes a little sodium chloride here. I'll do a little balancing like I'm in chemistry class maybe. But basically what happens is you actually have two sodiums. So each of these sodiums will donate one electron basically over to each of the chlorines, because basically in this case you have two chlorines, right? So each of those chlorines will actually pick up one electron, which will give it, this guy on this side, technically two Cl minuses. And when this guy loses the electron, that is when it becomes a positive charge. So in this case, it's actually the sodiums donating the electrons over to the chlorines. And when each of those chlorines pick up one electron, they each become negatively one charge. They also go for a swim basically in the solution at that point, and probably going to start swimming around if it's sort of aqueous in that case. The sodium, by the way, on the left-hand side does not have a charge. That solid sodium piece of sodium metal does not have a charge, again, until it gives away its electrons in the presence really of chlorine, as we'll talk about. Basically, chlorine has a lot of properties that make it want to accept electrons. And sodium has a lot of properties where it's like, just take my electrons. So those two guys coming together causes those two things to happen. It allows the sodium to give up its electrons because the chlorine is like, I want them. And the sodium's like, go ahead and take them. And then you get that transfer of electrons to occur.
Like examples, we're looking like in that equation that you just wrote out, or like the product side.
Yeah. So what we look at when we write the sort of formula, it essentially is the product of those two things coming together, the metal and the non-metal basically coming. Yeah. Yep. Other questions on that? All right. So if we look at a couple more examples here, that is barium with a +2, oxygen with a -2. So one of each of those is all we need. Once again, when we put it together, we get BaO. We do not have any charges on the ionic formula that we write. But again, really, it is made up of two things that do have charges. It's made up of a barium with a +2 charge and an oxygen with a -2 charge. In this case here, we have aluminum that is +3 and sulfide, which is -2. In this case, you want to think about the common number between that. Very simply, just multiply the two numbers together. 3 times 2 is 6, right? So basically, to get aluminum to 6, I need one more. To get this guy to 6, I need 3 of them. So you just add up what you got going on there. That's 2 aluminums. And that is 1, 2, 3 of those guys. And that will give us, again, our proper formula. Basically, the +6s from the aluminums are balanced out from the -6s there. We'll talk about when we get into bonding, but that's really the reason we do this. This allows everybody to sort of lose and accept the right amount of electrons to be pretty stable in that situation for an ionic compound. That's really ultimately what's happening here. And lastly here we have K plus and P3 minus. You can even multiply those together. That's 1 times 3 is 3. So to get the K to 3, you need 3 of them. You just need one of those. So you got 3 Ks and 1 phosphorus. And you just put it together like so, yeah. It's the best way to do it. Again, you don't want to always blindly just move things down. Again, works a lot of times, but there's a good amount of examples where you will get the wrong formula if you just kind of blindly do it. So it's better to think about it in terms of balancing it. And once again, when you do an ionic compound, you want to balance the charge to 0 in the simplest way possible. So for example, sodium chloride, I could also do Na2Cl2, but that would be the incorrect formula because you could do it much simpler as NaCl, right? So you want to do it in the simplest way possible to get it to 0. By the way, the name of those 3 on the bottom, barium oxide, aluminum sulfide, and potassium phosphide. Again, IDE for the negative guys and whole name basically for the metals in front. Yeah. Any questions on that? And obviously when we get to naming, we'll talk about the specific rules for everything. Little preview action there, I guess. Yeah. Any questions on that? All right, that wraps up chapter 4. So we're gonna go to chapter 11 now. We're gonna talk about modern atomic theory. Really in this chapter, we're going to talk about electrons, electron configuration, what happens as electrons sort of move from one energy level to the next. So let's get into that. So as we talked about in the last chapter, basically the atom, right, has that positive core, which is our nucleus. And that again is where we have our positively charged protons and also our neutrons that have no charge. The electrons, which are our negatively charged particles, are flying around that sort of empty space, sort of the electron cloud, if you will. As we'll talk about in this chapter, again, they are flying around pretty randomly. They're not flying around in pretty circles or anything like that. The nucleus, as we talked about, is very small compared to the rest of the atoms. So really the electrons make up most of that empty space that's flying around. So one of the earliest ideas is sort of what we're talking about in this idea of what's happening is kind of what we talked about when we did sort of that flame test experiment. If we have sort of different energy levels and we have electrons, for example, on a, say, lower energy level, and if that arrow represents an electron, and if we do something to it, for example, like we did in the flame test where you stuck it in fire and kind of added a lot of energy, obviously, to the atom at that point, that's going to excite these electrons, and these electrons are going to find themselves really probably elevated to a higher energy level. And as we talked about a couple of times here, in terms of energy, things really are not very stable in high energy. Things always are trying to achieve the lowest state of energy that's possible. So what's going to happen in this case is eventually this electron will kind of work its way basically back down, maybe not to the same energy level it started at, but to a lower energy level, for example. And because of this, there is that law of conservation of energy, which means we don't create nor destroy energy, which means the only way for that electron to sort of come back down to a lower state of energy is the atom itself will have to give off that energy in the form of a photon of light. And that energy will come off as a wave, basically. And as we talked about with flame tests, if that wavelength of that energy coming off is in the visible part of the spectrum, you will see colors. So I think maybe we talked about fireworks, and that's sort of the idea there. As you kind of explode those fireworks, again, a lot of energy as they relax back down. Again, it's giving off energy in a specific part of the visible part of the spectrum where maybe we see green or we see red or blue or what may be happening here. So Planck came up with this idea of basically what he noticed was he heated a lot of solids and he saw that atoms and molecules emit energy in really these whole number multiples. And what he referred to that is as a quanta of energy. And a quanta of energy for our purposes here is really an amount of energy that's required basically for an electron to sort of transition from one energy level to the next. So the idea of this is, for example, in most cases in terms of electrons, they will gain energy enough, for example, to get to this energy level or to get to this energy level. They will never sort of find themselves between energy levels. So as electrons, for example, transition from one energy level to the next, they will gain a certain amount of energy, which is known as a quanta of energy, a packet of energy, enough to make that transition fully. They'll never basically end up like halfway between. So they'll either gain or lose enough energy to sort of fully transition from one energy level to the next. And when we talk about quanta of energy and how electrons sort of do that, we'll see a picture of this a little bit later on as well, but it's sort of like the staircase idea. When you're walking stairs, right, you have enough energy to go from, this step to this step to this step. You usually don't go halfway up a step and go, I'm just going to rest here for a bit, right? Because you're going to fall. So, and same thing coming down as well, right? As you come down, right, you go from one step to the next. And that's the idea here of how electrons sort of transition with this idea of quantitative energy. They're able to gain or lose enough energy to fully make those transition. Now, right, just like steps, as we'll talk about, right, some people can maybe do 2 steps at a time, right, and maybe 3, maybe not more than 3, I suppose. But people could sometimes just do 1. And electrons transition that way. Some electrons will maybe gain enough energy to fully go up maybe a few energy levels. Some may go up just 1 energy level or 4 energy levels. So it does depend on how much energy that they get. So Planck developed this idea of quantum theory, and to understand it, we talk about radiation as well. And radiation basically is the emission of energy in the form of these waves. Again, basically the energy is going to be transformed through space in the form of waves, which carry a specific wavelength and energy associated with it. So when we talk about that, let's talk a little bit about some properties of waves. So a wave can be thought of a disturbing, vibrating, disturbing energy that kind of bounce you. The bird there isn't moving, but the wave is passing them by. So if you've ever been in the ocean, right, and you kind of sit there, you kind of wait for the wave, you kind of bounce up and down as the wave sort of passes you. And as you maybe been in there as well, some waves are stronger than others, right? Depending on how fast they're moving and stuff like that, they may carry a bigger punch. And that's just basically how energy sort of travels along the way. So when we look at a wave specifically, there's some points on it which is important to know. So when you look at a wave such as this, between 2 peaks or 2 troughs, that is lambda. That is the wavelength. And the wavelength is typically given in meters and nanometers and centimeters sometimes. Nano is 10 to the minus 9, right? Centi, right? 10 to the minus 2. And again, those are very common conversions. I would say for the most part, if you come across a wavelength, it's probably going to be in meters or nanometers. And again, the conversion between those is really important because we use that a lot in chemistry. The frequency, which is not really a V there, but it's a nu is the really name of that, but a lot of people call it a V because it kind of looks like a V. That is the frequency, and that is basically the number of waves that pass through a particular point per second. The unit of frequency is usually a hertz or a reciprocal second. So 1 over seconds are a reciprocal second. And by the way, that again is the same as a hertz. Like in your radio stations, you turn it to 95.5 megahertz, right? That is the frequency of what you turn your radio station to pick up the radio waves that are coming in to your car, for example. Amplitude is the vertical distance from kind of the peak of a wave to the midline. If you come down, that's the amplitude. And the speed of the wave can be usually given by taking the wavelength times the frequency. So in general, the speed of a wave is usually meters per second. And how we get to those units is wavelength is meters, frequency is 1 over seconds. So when you multiply them together, you get meters over seconds is typically what you get. We'll see a more reusable equation in a bit where they don't use this little u, but c, which is the speed of light, is sometimes used as well. Now, light does behave like electromagnetic radiation, which again is this emission of energy in the form of waves. And electromagnetic radiation sometimes has properties or characteristics of particles. And a lot of what we talk about, or you talk about with sort of quantum theory, is this idea of the dual nature of light. And the idea here is some things like waves can have particle-like function, so they can behave like particles. And particles, like for example, electrons that we'll mainly talk about in this chapter, particles can have wave-like functions and behave like waves in certain cases as well. So this sort of the dual nature of light where they both can kind of behave like each other. They both have properties of each other. And what we'll see later on in this chapter is, particle like an electron has a lot of wave-like function, which sort of describes how it moves around in an atom, for example. So as I talked about, we could think of a beam of light traveling through space as a stream of tiny packets of energy, which are referred to as photons. And there is a relationship between the wavelength of a wave and its energy. So typically speaking, the longer the wavelength, so if you have a wave that's kind of stretched out like this, has a lot longer of a wavelength. So typically the longer wavelength usually means it also has a longer frequency and it usually has lower energy. So something with a longer wavelength typically will have a much lower energy. And that's different than if you had a wave more like this where it just kind of goes, which a much smaller wavelength. Smaller wavelength will also have usually a higher frequency, and that usually will result in higher energy. So when you have that smaller wavelength, usually it's packing a much higher frequency and a much higher punch in terms of energy than something that's a little bit more spread out. It takes a little while to come, right? Questions on that there? Yeah.
Longer lambda and longer b.
Yeah. Yeah, so the frequency here, right, because it's a longer wavelength, it's going to take longer for it to kind of pass the same point. So it's more spread out. So a shorter wavelength will kind of be like this, right? Just keep going, right? So it's going to obviously pass a point in more seconds and times like that, yeah. So for example, if you remember, if you're sort of sitting there, for example, you're the X, right? The wave's going to pass you, right? So as this guy comes, it's going to pass you and then it's going to take a while, right, for the next one back here to get to you. As opposed if you were sitting here, as soon as this one passes, this one's going to probably be on you pretty quick, right? And hit you pretty quick. Again, kind of like if you're in the ocean, you know, if you get hit every 2 seconds, right? That's a much shorter wavelength than if the waves are a little bit more drawn out, right? You could kind of sit there and bounce around until the next one kind of comes. So when we talk about light and photons, like I said before, sometimes this will fall in the visible part of the spectrum where we do see colors like that Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. And again, depending on the wavelength, it might give you a different color. So we could think of something like yellow light as having wave-like function, but also as sort of a packet of energy, like little particles kind of moving through as well. And here's sort of the difference, for example, between red and blue. Which one has the longer wavelength here? It's going to be the red, right? And again, the wavelength here is going to be between here, for example, and blue has a much shorter wavelength. In terms of energy, right, in this case, red should be a lower energy than blue. And actually violet or purple is a much smaller energy in terms of all the colors. Red's actually the longest of all the colors. And even colors have different energy associated with them, depending on their color, because they will have a different wavelength associated with it as well. Now, when we calculate electromagnetic waves, the speed at which they travel is sort of consistent. It is, in this case, they want you in this school to remember this number here for the speed of light. Now, I apologize in advance because I probably will round to 3, but they don't want you rounding here, so I'll do my best to use all these numbers here. They want you to use 2.9979 times 10 to the 8. That is meters per second is the units. That is the speed of light, and that's what C represents. C is the speed of light, which is about, as you can see there, 186,000 miles per second. So that's moving pretty fast. And that is a constant that you should know and you always have available to you. So when you're dealing with electromagnetic waves, you can actually use this formula here. This is our speed of light, which is that number above. This again is our wavelength in meters. And this is our frequency in reciprocal seconds. And once again, our speed of light in meters per second. So when you use this equation, you need to basically make sure the wavelength's in meters and the frequency does need to be in 1/seconds to be correctly. So you can rearrange this equation. You could solve for the wavelength. The wavelength would equal C divided by the frequency. Or if you want the frequency, it is C divided by the wavelength. So if you know the frequency, you can figure out the wavelength of light. If you know the wavelength, you can figure out the frequency of light. Good news is it's the same rearrangement there, and C is again a constant, 2.9979 times 10 to the 8 meters per second. Questions on that there? All right, so why don't you try one here? What is the frequency for a wave with a wavelength of 4.68 times 10 to the minus 7 meters? Take a few moments there, see what you come up with. Okay, so let's take a look. So once again, our formula here is C is equal to our wavelength times our frequency. Once again, in this case, we are given the wavelength, which is 4.68 times 10 to the minus 7 meters. We always have, and again, they do want you to know this number, 2.9979 times 10 to the 8 meters per second as our speed of light. Obviously, in this case, we are missing the frequency, which is what we're looking for. We need to divide that basically to the other side, and that will give us basically the frequency is C divided by the wavelength. Putting our numbers in here, 2.9979 times 10 to the 8 meters per second divided by 4.68 times 10 to the minus 7 meters. This again is why we do need the wavelength in meters, so that it properly cancels out with our speed of light, which is in meters. So again, commonly sometimes you're given to it wavelength in nanometers, so you want to make sure you have that. We'll do that little division there. And we will look at 6.41 times 10 to the 14 units. The meters on top and bottom will cancel. Actually, when you divide this guy's still on the bottom. It is 1 over seconds, or you could write reciprocal seconds like that if you like. Or, by the way, that again is a hertz as well. Any questions? Yeah. Yeah, the S minus 1 is one way that you could write reciprocal seconds. It's just like a shorthand for the reciprocal seconds are the units of frequency, and that is also the same as a hertz. So it's a 1-to-1 conversion between those two. So I would say most commonly you're probably going to be given a frequency in reciprocal seconds like that. But second to that, you also are very commonly given frequency in terms of hertz. And they are some version of hertz as well. So for example, megahertz, like I said before, like your radio, and mega is 10 to the 6. So you would have to convert it to just plain hertz at that point. In terms of what I gave there at the end, it does as long as you took one of them. Yeah, you don't have to put them all three. So it's giving you options in terms of how you could do it. Yeah. But it does need to be, in terms of the second, in terms of the units there, it does need to be 1 over seconds, or you have to write the seconds with the -1. You can't just write seconds because that would be incorrect because it is 1 over seconds the unit. So you can't just leave it as just seconds though. Yeah. You can use hertz as well. It is the same. It's a 1-to-1 conversion. Yeah. Other questions? All right, let's try another one here. What is the wavelength in nanometers for a wave with a frequency of 5.6 times 10 to the 14 hertz? Okay, so let's take a look. So once again here, we're going to use our equation. Our C is equal to our wavelength times our frequency. In this case, we're actually given the frequency, which is 5.6 times 10 to the 14 hertz. Again, that is basically a 1-to-1 conversion with reciprocal seconds. So you can use, again, either of those units, in this case. Here we are looking for the wavelength. So we're going to rearrange this. Basically, it's the same rearrangement. We're going to take the speed of light over our frequency. Again, we do have our 2.9979 times 10 to the 8 meters per second as our speed of light, always given. You always have that number, but again, very rarely given to you in the problem, right? So again, it's just something you got to remember that you have that number sort of available to you. So putting in our numbers here, we're going to go 2.9979 times 10 to the 8 meters per second. We're going to divide it by 5.6 times 10 to the 14. If you want to pop it into reciprocal seconds so you can visually see that those units are going to cancel, that might be helpful. And if you do that there, you're going to end up with a number probably that has digits, I imagine. Let's see here. And we'll go 5, what we got there? Go 5.35 times 10 to the minus 7 meters. This is meters, so in this case, we do want nanometers. So nano again is 10 to the minus 9. That would mean in this case, one of the prefix, 1 nanometer, is 10 to the minus 9 meters. So we go 5.35 times 10 to the minus 7 meters. Do a little dimensional analysis action here. 10 to the minus 9 meters, which again is 1 times 10 to the minus 9 if you need to punch that into your calculator. Those guys will cancel. It's going to give us about 535 nanometers. If you want to go sig fig, since that's the only number we really have, I guess we could go 540 nanometers there, sig fig wise, yeah. Any questions on that calculation there? Okay. So like I said, nano, very common sort of conversion here with these type of guys as well. And mega for like hertz as well. Again, megahertz, oftentimes used sometimes. Any questions? All right, so speaking of that, as we're talking about again, pretty much in this chapter, the idea of as these electrons transition, they're going to give off that energy in the form of a photon of light, which will carry a specific wavelength. And that wavelength doesn't always have to be in the visible part of the spectrum where we actually see color. It could be in other parts of the spectrum where maybe we wouldn't see color, but we might see different things. So this is the electromagnetic spectrum, and you do need to kind of know it in a sense. So let's talk a little bit about it. When we look at the wavelength here on the right-hand side, that is a large wavelength. And over here, that's 10 to the minus 2, which is a small wavelength. So in terms of energy, which side here should be higher in energy? Yeah, the side where we have the smaller wavelength, right? So energy is high on this side, right? And energy is lower, is kind of lower on this side over here. So over here, we have, first off, we have radio waves, kind of a longer wavelength. Again, like I said before, like your radio in your car, they send out at a specific frequency, right? It gets picked up and you could hear things there. Not a lot of energy associated with that, which is why it's relatively safe. We shoot next to it there. Probably cell phones are in this range as well. We got microwaves. Microwaves, right, have a little shorter of a wavelength than say radio waves. Also means that the energy is increasing. It has enough energy to spin around water molecules really fast, so your pizza cooks in like 2 minutes, right, in the microwave, and you're good to go. Next is the infrared spectrum, part of the spectrum. That is where we kind of feel heat and stuff like that coming out there. So again, more energy. Next is the visible part of the spectrum. So this is the visible part of the spectrum. And this is where we see our colors, basically. So that is our, again, our sort of Roy, G, right, Biv, right. So in this case, as we roll kind of from right to left, as I mentioned before, we do see differences in energy. So as you can see here, kind of a red, orange, yellow, a little longer in wavelength, a little shorter in energy. When you're hitting into the green, blue, and violet or purple, a little stronger in energy, shorter wavelength. So again, in terms of the colors, also differences in terms of energy. I would say when we talk about nanometers, this part of the spectrum is typically how those numbers are given, the wavelengths, like, 800 nanometers, 700 nanometers, 495 nanometers, 500 nanometers. So visible part of the spectrum, a lot of times it's the part of the spectrum where you'll actually see those nanometers used in terms of their sort of wavelength. Now, next is ultraviolet. Stronger in energy, shorter wavelength, probably why we sunblock up, right? So we don't get too burnt out there from the UV rays that are coming off. X-rays, shorter wavelength again, stronger energy, why they throw a lead vest over you when they give you an X-ray, and probably why they step out of the room as well, right? So they don't get exposed to it. And gamma rays that we talked about in the previous chapter there, that is pure energy. That is as strong of a radioactive emitter that you could get. It is a lot of energy, no charge associated with it, but very small wavelength. So you do need to know, in terms of the electromagnetic spectrum, the order of these things in terms of longest wavelength to shortest, highest energy to lower energy, higher frequency to lower frequency. So you need to be able to put them in order based off of that. You also need to be able to do that for the colors as well. Yeah. So you need to be able to put the colors, the red, orange, yellow, green, blue, and violet in that order as well. Yeah. Say it again. A wave, a wave and an array. Array, array is like, for example, a gamma ray. They're kind of the same thing. It's just the way that they're described. So they're described a lot of times as a array when they have more of a wave-like function. And particles, for example, like alpha particles, like a stream of particles and stuff like that, more like that. Yeah. But they're basically, all these things will transmit energy through space in the form of like basically waves. Yeah. Other questions on that? All right, we will lay it up there for